these are the notes for lesson 3.6, solving systems of linear equations in three variables. In lesson 3.5, we looked at graphing linear equations in three variables, or graphing in 3 dimensions. Now we're going to look at solving systems to see where those intersection points are. If you remember, in the previous sections, we looked at solving systems of linear equations in 2 dimensions, so x and y, and we looked at 3 different methods for solving these systems of equations. So the first one we looked at was graphing. The second method we looked at was substitution. And the third method we looked at was elimination. So we talked about how all 3 of these methods would work when we're solving systems of equations. Some will work better than others depending on the equation, but all 3 methods will work. The same is true with 3 dimensions or 3 variables. However, we are going to focus on substitution and elimination as our solving methods. We had 3 different solutions when we were looking at systems of equations. The first was one solution, and that's where the lines intersect at one point, and that is our one solution. If the lines were the same exact line and they were overlapping, then that was infinite solutions. And if we had parallel lines, then that was no solutions. The same is true in 3 dimensions. There are 3 different types of solutions. The first is one solution, and that is when planes intersect at a single point. Now on page 177 in your book, there are some images that will show us these solutions so that we can kind of visualize what that looks like. So if you have your book and you can open to page 177, you can look at these images with me. If not, I do have them and I'm going to show them to you in the notes in just a second. So we know that from lesson 3.5, the graph of the linear equation in 3 variables is a plane. So 3 planes in space can intersect in different ways. If planes intersect in a single point, as shown below, the system has exactly one solution. So notice here we have 3 planes and they're intersecting at this single point. So that means that we have one solution. Our second form of solution is infinite solutions, and that is if a line is connecting all 3 planes. And again, if we look at the image, if the planes intersect in a line as shown below, the system has infinitely many solutions. So you'll see all 3 planes are intersecting at this common line. So again, that means infinite solutions. And the last is no solutions, and that is if the planes have no common point. Now there are 2 different ways that this can happen. If we have parallel planes, or what we call pairwise intersection. So let's look at the images for these. So again, if planes have no point of intersection, the system has no solutions. In the example on the left, the planes intersect pairwise, but all 3 have no points in common. So notice that 2 planes intersect here, 2 different planes intersect here, and 2 different planes intersect here. So they all intersect with one other plane, but never all 3 in the same point. And the other example is parallel planes, as you will see on the right. So the planes are never going to intersect because they are all parallel. So again, we have one solution, infinite solution, and no solutions, just like we did in 2 variables. We also had that in 3 dimensions as well. For example, when we're solving this system, when we are solving systems in 3 dimensions or 3 variables, we are going to be using a combination of substitution and elimination. So what we want to do is pick 2 equations that we can use elimination with, and then we're going to use 2 other equations to use elimination with, and then we're going to bring that together, and that will give us 2 variables, and we're going to use steps that we use for 2 variables from there. If we look at our equations, equation 1 and 2 can be easily changed so that we can use elimination. So if we start with the first equation, so 3x plus 2y plus 4z equals 11, notice that if we multiply our second equation by 2, then our y's will be eliminated. So if we multiply by 2, we get 4x minus 2y plus 6z equals 8. We're going to use elimination, so we have 7x, y's eliminated, plus 10z equals 19. Then we want to do the same thing with our last equation, our third equation, and either 1 or 2. Now, notice that we eliminated our y's in our first set of elimination. So we want to do the same with our second set as well. So in this case, we are going to use our third equation and our second equation. So again, if we use equation 3, we have 5x minus 3y plus 5z equals negative 1. If we multiply by negative 3, we get negative 6x plus 3y minus 9z equals negative 12. So 5x minus 6x gives us negative x. Again, our y's cancel out. Negative 4z, and that equals negative 13. So now notice that our two equations only have x's and z's. Again, you could have used a different combination of equations as long as the two that you get from your first step have the same variables. So if we would have eliminated our x's and our z's in our second one, it wouldn't have worked because again, we want the same variables. So now we're going to take our first equation, so 7x plus 10z equals 19, and our second equation, so negative x minus 4z equals negative 13, and we're going to use elimination to solve for one of our variables. So here notice that we have a 7x and a negative x, so if we multiply our second equation by 7, then our x's will be eliminated. So I have a 7x plus 10z equals 19. If we multiply by 7, we get a negative 7x minus 28z equals negative 91. Again, our x's cancel out. We get negative 18z equals negative 72. We divide by negative 18, z equals 4. Then from here, we're going to plug or substitute in to solve for x and to solve for y. So if we go back to one of our previous equations, so either 7x plus 10z equals 19, or negative x minus 4z equals negative 13, either one of those would work to solve for x. So we're going to plug in z. I'm going to choose the first green equation here just because it's all positive numbers. If we use the second one, we're dealing with negatives, and that's just not as fun. So I'm going to take 7x plus 10 times 4, because 4 is our z value that we just found, equals 19. So 7x plus 40 equals 19. Subtract 40 from both sides. 7x equals negative 21. Divide by 7 to solve, and x equals negative 3. So now we have our x value, we have our z value. The only other thing we need to solve for is y. Now in order to solve for our y value, we have to go back to one of our original equations. It does not matter which one we plug into, as long as we pick one of our original equations to plug back into. Here I'm going to use our second equation to plug back into. Again, we are solving for y. So I have 2 times, remember our x value was negative 3, minus y, because again that's what we're solving for, plus 3 times our z value is 4, and that equals 4. So I have a negative 6 minus y plus 12 equals 4. 12 minus 6 is 6. So I have a negative y plus 6 equals 4. And I'm going to have to go down here. So I have a negative y equals negative 2. And then if we divide by a negative 1, a positive y is positive 2. So now we have an x, y, and a z value. So our final answer is negative 3, 2, 4. And as always, we can plug it back into all three equations. It should be a true statement with all three of these variables, and it should be a correct answer. So again, our solution is negative 3, 2, 4. Again, we write it as a coordinate or a point, and we write our numbers in alphabetical order. For example 2, again, we're going to start out the same way. We want to choose two equations that we can use elimination with so that we can eliminate one of our variables, and then we're going to do the same thing with our second set of equations as well. So if you notice here, we can take our first equation. If we multiply everything by a -3, then that will eliminate our variable for the second equation. So we have a -3x minus 3y minus 3z equals -6. And our second equation is 3x plus 3y plus 3z equals 14. Now notice that this is going to eliminate all three of our variables. So our x's cancel out, our y's, and our z's. So this is all 0, and that equals 8. Now if you recall from our systems of linear equations with two variables, whenever we get a statement that is not true, so in this case 0 is not equal to 8, we know that that is an indicator that we have no solutions. So in this case, once we get to that statement, we know it's no solutions, and we're done. For the next example, again, we're going to start the same way. We want to eliminate one of our variables. If you notice our first two equations, we have a positive z and a negative z. So the z's are already going to cancel each other out. So we have x plus y plus z equals 2, and x plus y minus z equals 2. So our z's cancel out. We are left with 2x plus 2y equals 4. And then we're going to do the same thing. In this case, we're going to use our second two equations. Notice our z's are going to cancel out again. So we have x plus y minus z equals 2. 2x plus 2y plus z equals 4. Again, z's cancel out. We get 3x plus 3y equals 6. So then from here we want to use elimination with these two equations. So in order to eliminate either the x's or y's, we're going to multiply one equation by -3 and one by positive 2. So again, let's start just by rewriting these equations. So we have 3x plus 3y equals 6. And we have 2x plus 2y equals 4. Again, we're going to use elimination to get rid of one of our variables. So I'm going to multiply my top equation by 2, my bottom equation by -3. So this gives me 6x plus 6y equals 12. And our second equation, -6x minus 6y equals -12. Notice that our x's and our y's cancel out, and 12 minus 12 is equal 0 as well. Now this is a true statement. We get 0 equals 0, so we know that this is an indicator that we will have infinite solutions. So these are our two special cases. So again, if we end up with a true statement where everything cancels out, that is infinite solutions. If we have an untrue statement, we know that that is no solutions. So again, we solve systems with 3 variables just like we do systems with 2 variables. There's just a couple of extra steps that we need to use to solve.